Last class we left off, we were talking about stoichiometry. We got into our basics of stoichiometry, which is hopefully review for us. And we left off with this example, which I encouraged you to try on your own time, so we're going to rush through it. A component of acid rain is nitric acid, which forms when NO2, which is a pollutant, reacts with oxygen and water according to the simplified equation. We can tell that this equation is probably balanced because we have coefficients. So that's nice for us. We don't have to do any equation balancing, but we did learn how to do that last time for normal equations, quote-unquote normal equations, as well as for double displacement reactions where we had a slightly different method. The generation of the electricity used by a medium-sized home produces about 16 kilograms of NO2 per year. So that's some information that we're given. Assuming there's adequate oxygen and water, what mass of nitric acid in kilograms can form from this amount of NO2 pollutant? So we are looking for mass of HNO3 in kilograms. So going from kilograms NO2 to kilograms HNO3. So we've got at minimum 4 steps. There's not really a maximum, but hopefully we can do it in no more than 6 steps. One of those steps we could convert to grams of NO2. Likewise, on the back end, we could have gotten grams HNO3. From grams, we can go to moles using our molar mass. From moles of NO2, we can go to moles of HNO3, nitric acid, which would then get converted to grams of HNO3. To do kilograms to grams, 1 kilogram equals 1,000 grams because kilo equals 10 to the 3 or 1,000, so you swap in 1,000 for the K and you get 1,000 G. We're also going to need molar masses. And if I had thought ahead, I would have calculated these out ahead of time, but that's okay. We'll take a little bit of time to get those. So for NO2, it's that. For HNO3, we're going to add another oxygen and a hydrogen. It'd be 63.012 grams per mole. So starting with our 16 kilograms NO2, we convert that to grams by multiplying by 1,000. Kilograms cancel. Next step, we convert to moles. We divide by our molar mass. So grams goes on the bottom. That cancels the grams that are on the top. We're now in units of moles NO2. From moles of NO2, we can convert to moles of HNO3, and to do that we need the two things that we care about, the NO2 and the HNO3 from our balanced chemical equation. It's a ratio of 4 to 4. The one that we're going to goes on top, so 4 HNO3 on top. Optionally, you can also have the units of moles in there, but I'm in the habit of leaving it off, so I left it off this time. So the units that we have are moles HNO3, right where we want to be, based on our solution map. Then we multiply by our molar mass for nitric acid, HNO3. Moles cancel. And then at the end, we convert back to kilograms by dividing by 1,000. So after all this is said and done, we should be left with some number that represents the kilograms of HNO3. and it should be a relatively similar amount to what we started with. It should be like same general realm of numbers. We've got a 1-to-1 ratio for our moles. The molar masses are pretty similar, so we'd expect it to be pretty similar. If we got a crazy large answer or a crazy small answer, that would be a sign that maybe we didn't do something correctly. The number that I'm getting from my calculator rounds up to 22 kilograms nitric acid. If we tried that beforehand, or even if we didn't, we were just following along, are there any parts that tripped us up here? At its base, it's still a grams to moles to moles to grams problem. It's just that we started with kilograms. So grams to moles to moles to grams, that's one of our common solution maps for stoichiometry problems. With this type of problem, there's also something that we can do. Some of us will not want to do this because we'll forget. But since we're starting in kilograms and ending in kilograms, we actually don't have to convert the kilo away. Because if you notice, our first conversion factor, 1,000 grams over 1 kilogram, our last conversion factor is flipped. So those actually cancel each other out. So if you wanted to, kind of advanced tech, but if you wanted to, you can leave the kilo on there and it'll just follow all the way through. Just make sure that you don't forget that it's there. So that's why I say we probably won't want to do it, but advanced tech if you want to try it. All right, going back to our pizza recipe, remember that this is our pizza recipe for a cheese pizza. Let's say that we've got 4 crusts, 10 cups of cheese, 15 ounces of tomato sauce. How many pizzas can we make? So what we're getting at here is that there is going to be a limiting reactant. There's going to be something that runs out first. This is almost always the case. Very rarely will we not have something run out first. And so what we want to see is which of these ingredients will make the fewest pizzas, or which ingredient runs out first. What's holding us back from making more pizza? So if we look at crusts, 1 crust, 1 pizza, so starting with 4 crusts, we get 1 pizza out for each pizza crust that we put in. Four pizzas. Sometimes these are conversion factors you can do in your head. If we do cheese to pizza, we've got 10 cups of cheese. One pizza for every 2 cups of cheese. The cups of cheese cancel, 10 divided by 2. It would be 5 pizzas. And last but not least, we've got our tomato sauce. We've started with 15 ounces. We've got 5 ounces of tomato sauce turns into 1 pizza. So we do 15 ounces tomato sauce. It's 5 in. 5 ounces tomato sauce in equals 1 pizza out. So we would end up with 3 pizzas. And we've got this also displayed visually on the next slide. So we've got enough crusts that we could make 4 pizzas, because we've got 4 crusts. We've got enough cheese for 5 pizzas. We've got them grouped in 2 cups, and we've got 5 sets of those. And then our tomato sauce is all together, but we could only make 3 pizzas. So what we're learning from this is that tomato sauce, in the case that we're talking about in the class, runs out first. So tomato sauce runs out after 3 pizzas. Can we make 4 pizzas or 5 pizzas? No, why not?
Because there's not enough sauce.
There's no more sauce. Now we could, of course, throw cheese onto crust, and we could just throw cheese into the oven. That would be a horrible mess. But we wouldn't end up with a nice saucy pizza at the end. We would just have cheesy bread. And that might be good, but we're not trying to make cheesy bread, we're trying to make pizza. So the tomato sauce runs out after 3 pizzas, and so tomato sauce is limiting. I'm going to write it as TS. So that would be our limiting reactant if this was a chemical equation, and the 3 pizzas out is the amount that we would expect to make, and that is our theoretical yield. So tomato sauce is the limiting reactant. Limiting reactant, a couple ways of thinking about it. It runs out first, and it also, because it runs out first, limits the amount of product. Because it limits the amount of reactions that we can do. The maximum number of pizzas we can make is the theoretical yield. This is the number of, in this case, pizzas that we can make with our limiting reactant. So the number of pizzas possible with our limiting reactant. It says the maximum amount that we can make. And sometimes our brains, sometimes students' brains read maximum number and they're like, we're going to pick the biggest possible amount that we can make. So in this previous example, they would say, okay, 5 pizzas is our theoretical yield. We can't make that amount. That's not the maximum amount that we can make. It's actually the smallest amount of all of the totals that we come up with. So if it's confusing to you to think of it as a maximum number, theoretical yield is the smallest yield because the other things are going to run out, or one of the things is going to run out. So our limiting reactant determines how much we can actually make. The amount that we can actually make is our theoretical yield. In a chemical reaction, because this is not a culinary class, in a chemical reaction, we also can calculate limiting reactant and theoretical yield. So when one of our reactants gets used up, we can't make any more product. Reactants that are not completely consumed are said to be in excess. In excess just means we have extra. A lot of the time, we will expect to have some extra. But it depends on the circumstances, it depends on the reaction. There are probably some reactions that go on where they don't have any excess because both of the reactants are toxic or bad or dangerous. But generally, we are going to have reactants that we have extra. Related to limiting reactant and theoretical yield, we also have actual yield. Actual yield is what was made. You cannot calculate actual yield. You can only determine it from doing the experiment. Or, more likely on an exam, you'll be told what the actual amount is. So let's say that we're making our pizzas. We have a maximum that we can make of 3 pizzas because our cheese runs out after 3 pizzas. Cheese is our limiting reactant. Sorry, not cheese. Sauce is our limiting reactant, so we can make 3 pizzas with our sauce. But while we're cooking them, we burn a pizza, we drop one, our dog gets a hold of it, pulls it off the countertop, and we decide not to eat it. So we only get 2 pizzas out. So 2 pizzas survive the process. Actual yield is 2 pizzas. Typically, if we're doing a reaction, or if you're looking up scientific literature online for a reaction, they're going to report their actual yield. The actual yield is very important to report because it lets us know how much we can reasonably expect if we do it the same way that they did and if we're as good at whatever it is as they are. Relating to cooking, typically we're not going to have we will have a limiting reactant, but we'll expect to make a certain number of batches of cookies or whatever. And there will be a theoretical yield based on what they report in the recipe. Like, oh, this will make 4 or 5 servings. And then we might make it, and it turns out it makes more or it makes fewer servings depending on what we think a good serving size is. There's a monster cookies recipe that I really liked to make when I was in college. And the theoretical yield, I think they said that it was supposed to make 2 dozen or 3 dozen, and I always got like 4 or 5 dozen cookies out. So I always had way more cookies for some reason. I guess my cookie scooper was just smaller, or I was measuring incorrectly. Related to this actual yield, we can also calculate percent yield. And percent yield has this formula. So we take our actual yield over our theoretical yield, we multiply it by 100%. It's possible to report a percent yield that's above 100%. It's possible and more likely that you'll report a percent yield less than 100%. Your actual yield is typically less than your theoretical yield. Percent yield is also important because it lets us know how much we can expect to get out. It doesn't always scale nicely, so if we're trying to make like one small batch of cookies, we might get a really good actual yield compared to our theoretical yield. We might have like a 90% yield. If we're making 5,000 dozen cookies, there's a good chance that we'll make more errors in there because of the way the reaction scales up or the baking scales up. All the important points and terms that we need for limiting reactant and yields are all summarized on this slide. So these would be good things to have memorized. And we're going to be using these in some more problems. We'll be using them in lab as well. So our limiting reactant, the thing that runs out first. The reactants that are in excess, everything else. So things that we've got extra reactant. Our theoretical yield is how much we can make, assuming everything goes perfectly. Assuming we don't burn our pizzas or drop them on the floor. Our actual yield is the amount that we made, so -1 because we dropped a pizza on the floor or we burnt it. And then our percent yield is our actual yield divided by our theoretical yield times 100%. Usually our actual yield and theoretical yield will be in grams. So putting these into a chemical reaction, here's our combustion reaction for methane that we saw last week. So methane plus 2 oxygens turns into carbon dioxide and H2O. Let's say that we've got 5 molecules of CH4, 8 molecules of O2, which is the limiting reactant. 5 molecules CH4, let's do in red, are 8 molecules of O2. So for CH4, let's say that we're going to CO2. 5 CH4 is what we started with, 5 molecules of CH4. It's a 1-to-1 ratio, so we get 5 CO2s out. So 5 methane molecules turns into 5 carbon dioxide molecules. If we look at oxygen on the next slide, the number of CO2 molecules we can make from O2 molecules, we had 8 that we put in. Our ratio is 2-to-1. So 2 oxygen molecules in turns into 1 CO2 molecule out. So we do our 8 oxygens divided by 2, and we would be able to make 4 CO2 molecules. So in this example, oxygen runs out first. It has the smaller yield. You could also calculate this with water as your product. It doesn't matter which one you choose. You'll get the same end result, that oxygen runs out first. So despite us having more molecules of oxygen, right, we had 8 molecules of oxygen and 5 molecules of CH4, because of the coefficients, because of the ratios, we run out of oxygen first, even though we have more. So it's not always that the smaller amount runs out first. So oxygen, because it runs out first, is our limiting reactant, and 4 CO2 molecules is the theoretical yield. The amount we can make with our limiting reactant, LR. All right, looking at a different process and some images. Nitrogen and hydrogen gas, N2 and H2, react to form ammonia, NH3, according to this reaction. Is this reaction balanced? Any guesses? It is balanced. One of the ways that we could guess that is we've already got coefficients. Always good to check, but yeah, it should be balanced. So a flask contains a mixture of reactants, nitrogen and hydrogen. That's over here on the left. They're allowed to go through this reaction. Which of these following images, A, B, or C, best represents what's going to be left in the flask at the end? What's our limiting reactant, and which reactant is in excess? How would we start this problem? How could we start this problem? Finding the limiting reactant. How would we do that? Count the number of molecules. Yeah, so let's say that our hydrogens are red, and we'll make the nitrogens blue because they are colored in blue. So we've got 2 N2. For our hydrogens, we've got 4, 5, 6, 7, 8. So we've got 8 H2 and 2 N2. Our ratios for our nitrogen, 1 nitrogen turns into 2 NH3, so we're going to multiply by 2. So we would expect to see 4 NH3 produced. For our hydrogens, 3 in results in 2 out. So 3H2N, we get 2 NH3 out. So 8 divided by 3 times 2. It's going to be 5 1/3. We can't get 5 1/3 out because we're working with individual molecules. So we're going to have some left over for our H2. That's not the best place to draw that arrow. Okay, so our limiting reactant is our nitrogen. It's got the smaller yield. It's got a yield of 4 NH3. And hydrogen is in excess. We end up with a larger amount. That feels like the wrong number to me.
Where did you get 2 and 3? Besides in the picture.
2 and 3 up here?
Okay. 2 and H3. Okay.
So nitrogen's limiting because it's got the smaller yield. And we would be looking for a reaction that's got 4 NH3 in it, one of the flasks. Which flasks have 4 NH3 in them? B and C. So we've limited it to B and C. What's different about flasks B and C? C has some H2 in it.
Which is limited.
B doesn't have any H2 in it. H2, is it going to run out perfectly, completely, get used up, or are we going to have some left over? We're going to have some left over, and so C is our better answer here. H2 is in excess, some will be left over. Like we see in flask C. All right, when we get quantities of reactants and we're doing limiting reactant and yield, we want to calculate the moles of product from each reactant. So we're going to do grams to moles to moles. For every reactant. The moles that we get out is going to be our theoretical yield, but in moles. So in this example, we're looking at magnesium reacting with oxygen. We've got an amount of grams of magnesium we're putting in. We've got an amount of grams of O2 that we're putting in. So we'd set up our steps, convert grams to moles with molar mass. We're doing the same thing with oxygen. Then we do our ratio from moles of magnesium to moles of magnesium oxide, moles of oxygen to moles of magnesium oxide. And the number of moles that we get out here will be one of them will be our theoretical yield. One of these will be smaller than the other. The smaller amount is the theoretical yield. And we want to convert that to grams. This is the most efficient way to do it. There's a slightly less efficient way to do it, where you just do grams to moles to moles to grams for all of your reactants. So you'd have 2 or 3 full lines. All we're doing with this step, with this version, is we're saving ourselves doing this one final step however many times that we've got excess reactants. It's like 1 or 2 or 3 times. We can also calculate, if we wanted to, grams of product from each reactant. That's an if you want. It does take slightly more time. So we're going to do grams to moles of our product for reactant 1, for reactant 2. If we've got more reactants, we do it for those ones too. Whichever one of those numbers of moles is the smallest, we take that many moles of our product, turn it into grams. That's our theoretical yield. So using that example reaction scheme, we can do this problem. We've got magnesium and oxygen that we're starting with, and we're given a balanced chemical reaction we can make a good guess that it's balanced because we've got coefficients already. So we want to set up our two reactants in two separate lines. Our 42.5 grams of Mg and our 33.8 grams of O2. We need to convert these to moles so that we can use our balanced chemical equation. Our balanced chemical equation is always going to be using units of moles or molecules in some rare cases. So we find our molar masses off of our periodic table. I'll include the chemical labels for these as well. So our first step should look something like this. So we've converted grams to moles for both. And then we also have to do our ratio step. So 2 magnesium in will turn into 2 magnesium oxide out. These two numbers and the labels we're putting into as our conversion factor. We're starting with Mg. Mg is our starting chemical. So we put that on the bottom. I'll include the moles in there as well. And 2 MgO on the top. So our moles of magnesium cancel. We're left with moles of magnesium oxide. And to be maximally efficient, this is where we would stop for now. We're also going to do the same thing for our oxygen step. Our ratio is 1 oxygen in, turns into 2 magnesium oxides out. We'll do this with the blue underlines. So 2 mole MgO on the top, 1 mole O2 on the bottom. The moles O2 cancel with the blue strike through. And we'll take a pause and get those calculations. So the numbers that I'm getting on my calculator are these. Our magnesium can make 1.74 and change moles of magnesium oxide. Our oxygen can make 2.1 and change moles of magnesium oxide. Which of these two chemicals is going to run out first? The magnesium is going to run out first because it makes the smaller amount. So magnesium is limiting, or is the limiting reactant. We still need to figure out our theoretical yield. So this is the one extra step that we add on to finish out our grams to moles to moles to grams. So we have to multiply our moles of MgO by our molar mass, which is 40.309 grams per mole. Our moles of MgO cancel out. And our theoretical yield is 70.5 grams magnesium oxide. Like I mentioned on the previous slide, if you wanted to, You don't have to stop at this moles of magnesium oxide. You can run both of them to grams of magnesium oxide and pick the smaller of those two. You're just saving yourself basically one step, depending on how you do it. If you do it step by step, you're saving yourself a step. If you would have gone all the way through to grams of magnesium oxide, arguably it takes the same time. You'll get the same answer regardless of which way you do it. We're also told in the problem the actual yield is 55.9 grams. What is our percent yield? So for percent yield, we're taking our theoretical yields on the bottom. Our actual yield goes on the top, and we were told that that's 55.9 grams. And we multiply this by 100%. And this, we should actually be dividing by our full number. And our yield is 79.3%. Which is fine. Not especially good, I think, for this reaction. But for other reactions, this would be superb. Sometimes the percent yield is like under 50%. All right, I'm going to skip this practice one and give us this practice one instead because it's got more stuff in it. So I'll give us some time to work on this and then we'll move on. To hopefully save us a little time, I'm also going to give us the molar masses of all the different chemicals. All right, we're going to go speed racer through this. So 2 things that we're starting with. There's a couple of pieces of information that we're given. Typically, anytime you're given a number in a problem, that's something that you should pull out or you should take note of. In this reaction, Fe2O3, an amount that we're given, and an amount of CO that we're given react. Those are our 2 reactants. And we're told that this produces this much Fe. So produces means that this is our product. Iron, as a solid, as a metal, is our product. So this is the one that we care about. We don't actually care about CO2 in this problem at all. We want to determine the limiting reactant. So which of these 2 reactants runs out first or makes the least iron? What's the theoretical yield, the amount that's made from that Fe2O3 or CO? And what's our percent yield based on the amount that we were told we produced? So we're going to start off by calculating our limiting reactant. So 167 grams Fe2O3 and 85.8 grams CO. We need to divide by our molar masses. The grams will cancel, will be in moles. Then we also need the ratio of each of our reactants to our product. For our iron 3 oxide, it's 1 to 2. So we get 2 irons out for every 1 Fe2O3, iron 3 oxide, that we put in. For our carbon monoxide, it's 3 in to 2 out. So we get 2 irons as a product for every 3 carbon monoxides that we put in. And we'll pause our calculations after this step. This will tell us the number of moles that we make of iron. 2.09 and change moles of iron. And 2.04 and change moles of iron. Which of these two is smaller? The bottom one, right, the 2.04. That's from carbon monoxide. So what this is telling us is that CO is limiting. It's going to run out first. And then with this moles of Fe, we want to calculate grams of iron. That's going to be our theoretical yield. So we're going to multiply by 55.85 grams per mole. And we get a theoretical yield of 114 grams Fe, which is our theoretical yield. So we figured out carbon monoxide is our limiting reactant. Our theoretical yield is 114 grams. We just need to figure out the percent yield. And this is where the 72.3 that we were provided comes into play. So 72.3 grams Fe divided by the 114 and change that we got out. Multiply by 100 to turn it into a percent. And you should get 63.4% for your yield. Questions about any of the steps that we did there? If you want to run more practice problems, there are more practice problems, I'm sure, in the book. Alex probably has some, and Jonathan and Liz in the STEM room in the library can definitely help you with that, or you can come to my office hours, and I'd be happy to run through some more examples with you as well. All right, moving on to some types of reactions. Combustion reactions, we've talked about previously in this lecture. This was last class. We talked about it just very briefly. So combustion reactions are characterized by the reaction of a substance, some fuel source, wood, propane, methane, something like that. It reacts with O2 and it forms one or more oxygen-containing compounds, typically including water. Combustion reactions also emit heat, a common reason that we do combustion reactions. We cook using combustion reactions very frequently. You can also use an electric source, and there's probably some combustion going on elsewhere that's causing you to have that electricity to do your combustion, or your heating, rather, at home. For compounds that contain carbon, hydrogen, and oxygen, the products of complete combustion, perfect combustion, are always carbon dioxide and water. So things that are hydrocarbons that could also have oxygen in them always produce CO2. Why did I write containing twice? Always produce CO2 and H2O. So carbon, hydrogen, oxygen containing compounds burn with oxygen, O2, to form carbon dioxide, CO2, and H2O. This is important. If it's just carbon and hydrogen, that would be a hydrocarbon. I think that there's a sugar that's C6H12O6, several sugars. So this would be an example of something that burns with oxygen to form CO2 and H2O. Or any other functionalized hydrocarbon, a ketone, an acid, an aldehyde. Those would also burn with O2 to form CO2 and H2O. One of the fun facts that we get from combustion reactions is we've got water as a product. So if you've ever been driving your car, or driving a car or riding in a vehicle, and you stop at a stoplight or a stop sign, and there's a car in front of you. For some reason, it's a truck that's popping into my mind. You see the truck stopped in front of you. You're waiting, you're waiting, you're waiting. It's finally everyone's time to go. The truck starts driving and water just dumps out of the exhaust pipe. Or some liquid dumps out of the exhaust pipe and it's all over the ground. That is from the combustion of H2, or of the octane, the CHO containing compounds, with O2 in the internal combustion engine. Water is one of the products, and what's happened is it's condensed into the tailpipe, and now it comes out as a liquid. So if you've ever seen that happen, that's completely normal. It's expected. That means that the engine's running, is basically all that means. So I think that's fun. Maybe you don't think so, but that's okay. Let's write a balanced equation for the complete combustion of liquid, this. So we're doing complete combustion. We want a balanced equation. And we've got C2H5OH. We get one of these for free. One chemical for free. It was in the equation. C2H5OH. It's a liquid, so we give it the little L behind it. What's another thing that's going to be involved in combustion as a reactant? O2, oxygen as a gas. Are there any other reactants in combustion? Hopefully not. So we put our arrow in. What's one of our products for complete combustion?
Gas, H2O.
We have H2O as a gas. And what's our other one? CO2, carbon dioxide. We also produce CO2 from breathing. So this is our skeletal equation. You will be expected to be able to produce such a skeletal equation on an exam if I were to give you an equation that's very similar to this, just probably with something that's not ethanol. It might be something bigger. It might be something smaller. It's probably going to be 3 or 4 carbons if I had to guess. So we've got our skeletal equation. Now we need to balance it. We're going to balance it by balancing things that are in one compound on both sides, basically we're just leaving our O2 to balance at the end. O2 is oxygen all by itself. We can change the number, the coefficient in front of oxygen, without affecting our hydrogen or our carbon. I usually just balance things left to right. So that means we're going to be balancing our carbon first. Our carbon, we've got 2 on the left side. We currently have 1 on the product side. That's a problem because our carbons are not balanced. If we add a coefficient of 2 in front of our CO2, that brings our carbons up. Now we've got 2 on both sides, nice and even for carbon. How many hydrogens do we have on our reactant side? We have 6. Because we've got 5 plus 1. We've got C2H5 OH. And the H here is also a hydrogen, so we have 6 hydrogens. You could, if you wanted to, write this C2H6O. That would be fine. That would be acceptable. And that makes it a little bit more obvious that we have 6 hydrogens. So 6 hydrogens on the reactant side. How many do we have on the product side?
2.
We have 2. Is that enough?
No.
It's not enough. We need a 3 in front. That multiplies by the 2, so 3 times 2. We've got 6 hydrogens. Now we're balanced up for our hydrogens. 6 on the left, 6 on the right. Last one to balance. Oxygen. How many oxygens do we have on the reactant side?
3.
We have 3. We have 1 oxygen in C2H5OH. And we've got 2 in our oxygen. And on the product side, we've got 3 times 1, 2 times 4.
7.
So we have 7. We can adjust our oxygens freely with our O2. How many oxygens do we need to gain to get 3 to equal 7? We need 4 more oxygens. What would 4 more oxygens, how many O2s would that be?
8.
If we need 4 oxygens, how many O2s do we need?
2.
We need 2 more,
4. Oh, yeah.
which is going to put a 3 in front of our O2. If we wanted to, we could make a whole algebra thing, and I think I'll go ahead and do that actually.
I see what you mean.
So here's the algebra. We've got 1 oxygen in our ethanol. Our O2 needs some number in front of it. And we've got a subscript of 2. So that's where this 2 that I'm putting in front of the X comes into play.
Okay.
X is going to be our coefficient. So that's the number that goes in front. On the product side, we can just write it in as 7. We already did that math. We don't need to redo it. So 1 plus 2x equals 7. We subtract 1 from both sides. 2x equals 6. Divide both sides by 3. X equals 3. Sorry, divide both sides by 2 and we get x equals 3. So our coefficient would be 3. You could also, if you got into this situation, just see, okay, what if we put a 2 in front? Is it equal then? What if we put a 3 in front? Is it equal then? If you end up missing your number, then you have to use a fraction. And then you multiply everything by 2. Questions or confusions about any of the steps here? This is slightly more confusing than if we just have a hydrocarbon because of the added oxygen in our fuel source. So a little bit more confusing. As long as you remember to count the oxygen, as long as you remember to count the hydrogen, you should be able to work through it. Some other reactions that we'll talk about now. Alkali metals will react with nonmetals, and they are vigorous, they are exciting, they are energetic. So alkali metals, we're abbreviating those as M, will react with halogens. Where do halogens live on our periodic table? What column do they live in?
So the second
7A or 17. So on our periodic table, right, second to the last column, those are our halogens. Where do our alkali metals live? 1. They're 1 or 1A. 2 or 2A is alkaline earth metal. 2 is bigger than 1. Alkaline earth is longer than alkali. So alkali metals, group 1, react with halogens, group 17/7A, according to this general reaction. 2 metals, 1 molecular halogen makes 2 MX. Sodium is an alkali metal, chlorine is a halogen, and this is typical of this reaction. It produces sodium chloride, so 2Na plus Cl2 turns into 2NaCl, and it produces heat and sparks. Making salt from elements is apparently exciting. Reactivity increases as you go down group 1. Lower alkali metals are more reactive. Up until you get to cesium, cesium is the most reactive of the bunch, and there's not enough francium that you could do the reaction anyway. So this would be a good one to know. Alkali metals will also react with water. Alkali metals react with water. They form a dissolved alkali metal ion. So the metal is a 1+ charge ion because they're alkali metals, so they form a 1+ ion. It'll also form hydroxide ion and hydrogen gas. These reactions are highly exothermic, and because they produce a lot of heat, this hydrogen gas that they produce can ignite or explode. So adding lithium to water, it's bubbly, it's fizzy, it's making gas. That's the H2 that we're seeing as the gas. Sodium's producing enough heat that it actually catches on fire, and that metal will dance around the surface of the water. Potassium produces an even stronger reaction, and if you move down to rubidium or cesium, they would have an even more intense reaction. I think there's a video of somebody throwing a little encapsulated pellet of cesium into a bathtub of water, and it big explosion. So that might be fun to go find. Maybe I'll find it and show it to us in lab or something. So more stuff to memorize. On this previous one, I'll leave up the equation so that we can write that down. Royal Society of Chemistry has a video of cesium and fluorine reacting. It's from like 10 years ago, but that's a cool reaction. It's a cool video. It's like 10 minutes. They talk about making the cesium, making the fluorine. Fluorine, they're making F just by itself, not F2. it's highly reactive, so they have to generate that like in glassware, because if it gets out, that's bad. It would react with stuff immediately. So they react both of these together, and it produces a really fun reaction. I think it's a fun watch, but I'm also a chemist, so I would. Halogens are among the most reactive nonmetals. Halogens will react with many metals to form metal halides. Those have this form. And they'll react with hydrogen to form hydrogen halides. These are not like particularly profound reactions, because the MX with the subscriptive N, this is just like, it depends on the charge of the metal and the nonmetal. Like you could probably come up with this, as long as you remember that the halides or the halogens are diatomic. F2, Cl2, Br2, I2, etc. As long as you remember that, and you can come up with the neutral ionic formula, you should be able to come up with these halogen reactions. And the hydrogen halides contain covalent bonds because hydrogen's a nonmetal, the halogens are nonmetals. They'll form acids when you combine them with water. So when they're aqueous, they'll form acids. Write a balanced chemical equation for each of these reactions. We've got a reaction between aluminum metal and chlorine gas. What is aluminum metal going to be?
Al, 30 plus.
Al, solid. In its normal natural metal state, in cans, in our phones maybe, it's just Al as a solid. And what is chlorine gas?
Cl.
Cl.
G.
It's a gas, that's true. 2, Cl2. If we're combining chlorine and aluminum, what charge is aluminum going to have when it's an ion?
3 plus.
3 plus. And what about chlorine? What's its charge going to be? Cl minus. So if we swap and drop these, our product will be Al Cl3. As a solid. And then you could balance it from there. So this is one way that you could come up with it. They're going to form an ionic compound because we've got metal and a nonmetal. So we're going to get an ionic compound. So we'd have 2 there, and 3 there. We want a reaction between lithium metal and liquid water. What's special about reacting alkali metals with water? What's fun and exciting about them?
Boom. Gas.
Explosions, burning, something like that. What's burning?
The sodium. I mean the.
It's the gas that's burning. So we've got lithium metal, that's a solid. We've got water, H2O, that's a liquid. We are producing the metal as an ion. We're also producing hydroxide. We're also producing H2. The H2 is the part that burns. The lithium ion and the hydroxide are both aqueous. The H2 is as a gas. And then to balance it, we need some 2s. I think we use 2s in front of both the metals as well for charge purposes. All right, and then what about a reaction between gaseous hydrogen and liquid bromine? What is gaseous hydrogen?
H2.
H2 as a gas. And liquid bromine is what? Br?
BR minus 2 minus.
Also 2. And when those react, hydrogen's going to be a +1, the bromine is going to be a 1 minus, so it'll form HBr. I'm assuming that this will be a liquid. And to balance it, we need a 2 in front of the HBr. So I would say the one tricky one is the alkali metal reacting with water. The other examples, we're making an ionic compound. You can figure out the formula based on the charges, and then you can do the balancing work after that. The important point that we need to remember for all of these is some of these halogens, all the halogens are 2s. Hydrogen's also a 2. Using any number of our mnemonics, H7, Brinkelhoff, or the very applicable horses need oats for clear brown eyes. I think in the past I've given 1 or 2 of those as multiple choice questions. Questions about chapter 4? Cool, we'll stop there.